So when we look at this integral, we obviously can't do it by inspection, or at least I definitely can't. And you might perhaps think to try using integration by parts, but that would mean you would have to factor off a factor such as power of tangent, but the integral of tangent is log of sec, and that's not going to be very nice, multiplied by the derivative of tan cubed. And I don't immediately know how to integrate tan squared or tan cubed either. So I don't think either of these methods is going to work immediately. Instead, what I think you ought to do is to remember the key algebraic identity that sec squared theta is 1 plus tan squared theta. And this identity should always be in your mind as being potentially useful if you have anything to do with tangents or secants. And just rewriting this immediately, we also see, of course, that tan squared theta is equal to sec squared theta minus 1. So let's substitute this identity in here for one of the two powers of tan squared that make up tan to the fourth. So in other words, we can rewrite our integral as the integral from 0 to pi over 4 of sec squared theta minus 1, that's tan squared theta, multiplied by tan squared theta, integrated with respect to theta. We could use it for both, but that would seem a little bit like overkill. Let's do it one step at a time and see what happens. So now, if we look at this, we see that effectively we've got two integrals. We've got the integral of sec squared theta times tan squared theta, and we've got minus the integral of tan squared theta times 1, so the integral of tan squared theta. Now, surprisingly, if you think about it, the first integral, sec squared theta times tan squared theta, is easier, and we can do it by inspection. And this is because sec squared theta is the derivative of a tangent, so we have a function to a power squared multiplied by the derivative of the function. So we can do that by inspection. So let's just do this. So we have the integral from 0 to pi over 4, and then it's sec squared theta tan squared theta d theta. That's going to be an integral we can do by inspection, minus the integral from 0 to pi over 4, and then it's just the integral of tan squared theta d theta. So now we're going to take two different routes. This we do by inspection. This one, we can use this identity again, because if we rewrite tan squared theta as sec squared theta minus 1, well, we know how to integrate sec squared theta. It's just tangent of theta minus, and the integral of 1 is theta. So what we're going to obtain from our first integral here is going to be something like tangent of theta, but to a higher power. So we increase the power by 1 tan cubed theta. And now if we differentiate that, we will pull a factor of 3 in front, and we don't want that, so that's easy. We'll just put a factor of a third in front to mop it up. And then if we differentiate, the 3 comes in front, cancels with that. We reduce the power by 1, we have tan squared. And then from the chain rule, we multiply by the derivative of the function that was raised to the power, and that was tangent, and the derivative of tangent is sec squared. So if you differentiate that, you get that. This is therefore the integral of that. And this is between 0 to pi over 4, minus the integral 0 to pi over 4 of sec squared theta minus 1 integrated with respect to theta. So now, I know that the tangent of pi over 4 is 1, but I'll just write it out slowly. So it's 1/3 tangent cubed of pi over 4 minus 1/3 the tangent cubed of 0. And I didn't bother opening a big bracket after the minus sign and writing down the function here at the lower limit because there's just one term. And then we have minus, and the integral of sec squared is tangent because the derivative of tan theta is sec squared theta, minus theta because the derivative of theta is 1, and that's between 0 and pi over 4. So the key things that we need to recall are that the tangent of pi over 4 is equal to 1, and the tangent of 0 is equal to 0. So this tells us that at the lower limit, when theta is 0, everything is going to vanish. We just get contributions from the upper limit, theta is pi over 4. So what we're going to obtain is that our integral is equal to 1/3 times 1 cubed minus 0 minus, and now I'm going to evaluate this at the upper limit, and because there's a minus sign outside, I'm going to open a big brackets. So that is minus, open brackets, and then the tangent of pi over 4 is 1 minus pi over 4, and there is no contribution from the lower limit because this all vanishes when theta is equal to 0. So this tells us that we have 1/3 minus 1, so that's minus 2/3, and minus minus is plus pi over 4. So what we see is that the integral from 0 to pi over 4 of tangent to the power of 4 of theta with respect to theta is equal to pi over 4, and putting the positive term first, minus 2/3. And that is our result for this integral. So let's just quickly look at what we did. So we looked at this integral and we thought the simplest way to do it was to use this identity here. And we said tan to the 4th is tan squared times tan squared, and we substituted this identity into one of the tan squared powers. And then we had two integrals because this is a difference of two terms. This integral we could do by inspection. This integral we use the identity again. All the contributions came from the upper limit, and this is our answer. Now, something we can immediately think about is our integrand here is raised to the is a function, the tangent raised to the power of 4. It is therefore always going to be greater than or equal to 0, so it's positive or 0. So the integral from 0 to pi over 4 of something which cannot be negative must be positive. So if we've got that right, this combination must be positive. Pi over 4 is a little bit more than 3/4. 3/4 is more than 2/3. So we immediately see that this is positive as we would expect. And if we'd made a minus sign error and obtained a negative answer, we'd know that we'd made a mistake. So on the next slide, I'm going to look at this integral and just see quickly how differentiating the result for the indefinite integral works and shows us that we're correct as well. Okay, so let's move on to the next slide. So on the previous slide, if you trace it through, you'll be able, I hope, to convince yourself that the result for the indefinite integral of tan to the fourth theta is a third tan cubed theta minus tan theta plus theta. And I just want to differentiate that and show it yields this. If you haven't done it already, you might want to pause and just check it yourselves. So what you obtain is, from here, you bring the 3 in front, cancels with that, reduce the power by 1, you get tan squared times the derivative of tan, and that gives you sec squared. So we have from the first term tan squared theta sec squared theta. From the second term, the derivative of tangent is sec squared theta. Let's be careful about the fact there was a minus sign here. And then differentiating this gives us plus 1. So what we have is a common factor of sec squared theta in these two terms. So that is tan squared theta minus 1 all times sec squared theta plus 1. Sec squared theta is 1 plus tan squared theta. I'm trying to write everything here in terms of powers of tangent because that's the original integrand just in terms of powers of tangent. So this is tan squared theta minus 1 times tan squared theta plus 1 from our identity. And then there is this plus 1 at the end here. And now we have tan squared theta minus 1 times tan squared theta plus 1, and multiplying that out, the cross terms will cancel. This is a very standard, useful algebraic identity. A minus b times a plus b is a squared minus b squared. So what we get is tan to the fourth of theta minus 1 plus 1. The 1's here, of course, are going to cancel, and we are left with tan to the fourth of theta, which is our initial integrand. So therefore, we are happy. This is as expected. So just to return to the definite integral, I just want to comment on why the tangent of pi over 4 is 1, and I'll do that on the next slide. So there are two triangles which we can draw for which it is relatively straightforward to obtain the trigonometric functions. The key one that we are talking about in this video is an isosceles right-angled triangle. So this is a right angle. These two angles are the same. That means these sides have the same length. The angles in a triangle add up to pi, so it's 180 degrees. But if we are using calculus, we must use radians. So this is going to be a right angle, and that is pi over 2. So these two angles add up to pi over 2, and that means that they are both equal to pi over 4. So now, the trigonometric functions are ratios of sides. So we could scale this triangle up and change the length, but to make and still get the same values for the trigonometric functions. But to make life as simple as possible, let's just say that this side has length 1, this side has length 1, and then by Pythagoras' theorem, 1 squared plus 1 squared, so 1 plus 1 is 2, is the square of this hypotenuse. So that means that this is root 2. So therefore, we see that the tangent of pi over 4, which is the opposite over the adjacent, is going to be equal to 1. And similarly, the sine of pi over 4 is the opposite over the hypotenuse, so it's 1 over root 2, etc. So if you're unsure about the trig values of angles like pi over 4, for pi over 4 in particular, you just need to draw this triangle and you can just read it off. The other triangle, while I'm at it, is an equilateral triangle. So if I draw an equilateral triangle, all three sides are the same. The angles are going to be the same. So that means that all of the angles are going to be pi over 3, so that we can add them up to obtain pi. Now, this is not a triangle with a right angle in it, but what we can do is we can drop a perpendicular, and if we drop a perpendicular here, like this, this is now a right angle triangle, and this angle here is pi over 6. So again, we could choose arbitrary scalings of this triangle, but let's try to make life as easy as possible. So to do that, what I'm going to do is say I'll choose this side of the triangle to be 2. So if I say this is length 2, that means that this, remember this line has been bisected, this line here has length 1. And 1 squared from Pythagoras' theorem, 1 squared plus the square of that is equal to 2 squared, which is 4. So 4 minus the 1 from 1 squared is 3. So this is the square root of 3. Check it with pencil and paper if you need to. So therefore, for example, the tangent of pi over 3 is root 3, because it is the opposite over the adjacent. And all the trig functions of pi over 3 and pi over 6 can be read off from considering this triangle. Okay, to conclude this video, what I would like to do is just to give you a couple of exercises with answers that you can look at afterwards. And I'll do that on the next slide. So here are two exercises for you which are somewhat similar to the exercises we've looked at in this video. This integral here, I hope you agree it has to be positive. This is the answer you should obtain for it. It's not immediately obvious that this is positive actually, even if you put it on a common denominator. But if you would like to verify it, you could use a calculator, I suppose, or you can find on the internet proofs that pi is less than 2 root 3, from which it follows that this is positive. And this integral here is an indefinite integral, and that's the answer that you should obtain. With that, I'll stop this video.